I want to introduce something else now relating to gravity called gravitational fields. I got a board marker in my hand right now, and we know that this board marker experiences a force of gravity caused by the curvature of space-time that the Earth causes, right? The Earth dents the fabric of space-time, and that causes a force of gravity between the Earth and the board marker. So the board marker is pulled down towards the Earth. Okay. Gravity causes that force. But what if that board marker is not there? What if it mysteriously disappears? What if I'm a magician and I make the board marker disappear? Watch this trick. Hey, watch it. I'm going to, on the count of 3, make the board marker disappear. Okay? Okay, on the count of 3. Okay? It's going to mysteriously disappear into nowhere. All right? Count of 3. 1, 2, 3, go. Whoops. That didn't work out so well. Okay, pretend it's gone. Now it's gone. Look, it's gone. Board marker's gone. What's the force of gravity on the board marker at that spot in my hand right now? 0, because the board marker's not there, right? Does that mean gravity has disappeared? No, not at all. The Earth dents the fabric of space-time. We talked about that a little bit the other day, right? The dent in the fabric of space-time is caused by the Earth, and that's still there, whether or not the board marker or anything else is there to experience that dent in the fabric of space-time. When you go tobogganing on a hill at, you guys go tobogganing at Morris Gibson School? How many people have ever gone tobogganing over there? Yeah? Okay, that's kind of the hill in Okotoks where people go tobogganing, right? You drive by there sometimes and there's nobody tobogganing in the wintertime. It doesn't mean the hill isn't there, right? The hill is there whether or not there's somebody experiencing the hill. Gravity is here whether or not there's something experiencing the gravity. But we've got to quantify it in a different way than we usually do, or at least in a different way than we have up until this point. Up until this point, we've talked about the force of gravity. There is no force of gravity if there's nothing to be pushed or pulled. So when the board marker disappears, the force of gravity disappears, but gravity doesn't. The way we're going to quantify gravity in this respect to illustrate for us that gravity is still there even when there's nothing to experience the gravity. In other words, to illustrate that the hill at Morris Gibson School is still there even when there's nobody sliding down the hill, is to invent this concept called gravitational fields. In general, a field, and there's different kinds of fields. In general, a field is a region in which a force can be experienced. So right there where the board marker was a few minutes ago is a region in which a force can be experienced. Maybe there's a board marker there actually experiencing a force. Maybe there's not. But it's a region in which certainly the force can be experienced or could be experienced if there was something there to experience it. So specifically, when talking about a gravitational field, it's not just any region or any force or any object. It's a region in which a gravitational force could be experienced by an object with mass. We'll define an electric field next year as a region in which an electric force could be experienced by a charged object, or a magnetic field as a region in which a magnetic force could be experienced by a magnet. But for now, gravity. A region in which a gravity force, a weight, could be experienced by an object with mass. So in other words, it shows us the influence of something producing gravity. In a context of the example that I was giving you, it shows us the influence of the Earth. The influence of the Earth. Not the force that's felt by the board marker, but the influence of the Earth. In other words, it's kind of showing us how much is space-time curved, right? How much is space-time dented by the Earth? Kind of. Now, to have a field, the gravitational field, all you got to have is whatever it is that's causing the field, right? The Earth, in the example that I just gave you, causes the field. Okay, that's all you got to have. To have a force, you need to have a field. In other words, the region in which a force could be experienced by a mass, but you also have to have an experiencer. So think of the hill at Morris Gibson School again. You drive past, and there's somebody sledding down that hill, tobogganing down that hill. There is a field. In other words, there's an influence or a region in which the tobogganer could be influenced, could experience a force. In other words, there's a hill there, right? You need the Earth to have the hill. In order to have the force, though, we need to have not only the hill, but we need to have the person tobogganing on the hill. To have a gravitational field, we need something to cause it. To have a force, we need something to cause it and to experience it, to feel the push or the pull that we define as a force. Gravity fields are vector fields because they influence masses in a direction. Right? If I put the board marker right here in this gravitational field, it's influenced. But it's not just influenced in a random direction. It's influenced downwards. Specifically, objects will move in a particular direction, experience a force in a particular direction as a result of a field. All masses will experience a force in the direction of that field.